Okay, so it is my great pleasure to introduce Catharina Stroppel, who will give the final talk for this workshop.
Okay, thanks very much. Thanks in particular to all the organizers, Michelle and Liz and Dusa, who organized this big event. And also thanks to everybody who really took part in the exercise classes and tried to learn all this stuff. So it was lots of fun also for me. So after all this complicated categorical stuff, I would like to give an application of this, and at the same time, make it a bit more complicated even, and give you a glimpse of categorification. So let's start from the beginning. So what I want to do is I want to use these web categories, which I introduced yesterday, to say something about knot theory. So in other words, I want to control, in some sense, knots via web stations here. So here you see a picture of a knot or two knots. So the definition of a knot is just an embedding of S1, so just a circle, into R3. And by a link, I mean a union, disjoint union of knots. And so what we would like to do is we would like to find invariants of knots. So a knot invariant with values in X, and X could be whatever you think of. So we don't know at the moment what X is a function which takes knots and looks at them up to isotopy or isomorphism if you want. And since for every knot, we want to have a value in X. And if two knots are isotopic or isomorphic, I want to get the same value. So we are more or less doing the same thing as we did in the first lecture. We want to classify isomorphism classes of knots. So now you can ask the question, how can we find such a thing? And of course, you can do something very stupid. You can just take X to be a point, and you send every knot to the same point. Of course, then two knots which are isomorphic or isotopic are sent to the same thing. And so this is such an invariant. But of course, it's a bit stupid invariant because it would not distinguish anything. So ideally, we would like to distinguish all the knots up to isotopy. But this is, on the other hand, maybe too difficult. So at the end, you might decide we do something in between, something which is still handleable, but still good enough to distinguish some of it. So, and to make a connection to what I did before, I want to use diagrammatics to construct such an invariant. I want to turn the knot into diagrams to define an invariant. Okay, and this is done by a projection onto the plane. So here's an example of our knot, and we can project to the plane. And what you see here, so I drew these three planes here, and it of course depends on which plane you project, you would get a different picture. So the same knot might give you different pictures depending on your project. So now the question is, when I have this picture on the plane, and I would actually draw it more carefully by really keeping track of the under and over crossings, something like this. So I want to say, given two such pictures, such diagrams of the knot, when do they represent the same knot? And so ideally, I would like to classify at the end knots in terms of classifying the diagrams. So ideally, we would like to have a list of each knot, a representative in terms of a diagram, and then maybe a name attached to this knot. So this is the ideal goal. And so on the way, there's the theorem of Reidemeister, which I think was mentioned in the session on Sunday. Two knot diagrams. So these are the diagrams obtained by projecting a knot to the plane. So let's say D and D prime represent the same knot. If they differ, if and only if, they differ only by certain moves. So if they differ by a finite sequence of isotopy moves in the plane, So that means you can just move them a little bit around in the plane. And what is more important, and of the following Reidemeister moves. So this is what are called Reidemeister moves. So what are these moves? So these moves are, you have your knot diagram, and you might change it slightly locally. So for instance, when you have a little curl, you can just pull at the ends and you make it straight. And it could also be the other curl in the opposite direction. Or if you have a strand going over another one, you can pull them apart to make them two strands next to each other. Or you have this sort of braid relations move, which we saw already several times. So for instance, let's check. So for instance, when I have something like this guy, so this complicated, stupid loop, I can use an isotopy in the plane. So this is equivalent to just this thing. And then I could use the first Reidemeister move, Reidemeister 1, and then it gets just this thing, which is the trivial knot. So this would be an example that this diagram at the beginning represents just the trivial knot. So, and then Kauffman had a great idea to construct a knot invariant using the diagrammatics, which is very similar to the temporally-Lieb algebra. So his idea is the following, and it's called the Kauffman bracket. So given a link diagram or knot diagram, D, then we define the bracket, the Kauffman bracket. So that's a Laurent polynomial with coefficients in Z, and is defined as follows. So we define it recursively by saying if I just take the empty link or not, so which is just by definition nothing, I just define this as 1. And then whenever I have a link diagram D and I add a trivial knot, then I just do the following thing. I multiply the value of the Kauffman bracket for D with Q plus Q inverse. And now you should maybe recall that the temporally-Lieb algebra for delta equals to this value was a very nice version. Namely, it was a quotient of the Hecke algebra. And so this was a nice choice of value for delta. And so this corresponded to our circle in the temporally-Lieb. So this is already first connection to temporally-Lieb. And then whenever I see a crossing, I can smoothen it. And I can smoothen it in two ways. So I can replace it by two strands which don't cross anymore in this direction, or I can replace it by two strands in the opposite direction. And I just take the linear combination with a Q in here. So, and if you have done this exercise, which realized the temporally-Lieb algebra as a quotient of the Hecke algebra, you saw that the Hecke generator was mapped to the temporally-Lieb generator minus Q times the identity. So what you see here is exactly the Hecke algebra expressing in terms of the temporally-Lieb quotient expressing in terms of the Hecke algebra. So this is a formula which appears very naturally from this diagrammatics categories. So now we can check whether this is an invariant. So for instance, let's check whether the Kauffman bracket of this knot is the same thing as the one which I get when I apply a Reidemeister 1 move. So let's just apply the rule of the Kauffman bracket. So I take the crossing, I replace this crossing by these two smoothings. So I write them like this, and then I close it. Okay, and then the second one gets subtracted with a coefficient Q. And then I can use this formula to say this is just a circle times nothing. So this would just give me Q plus Q inverse. And the other one gives me Q, and then two circles, which is Q plus Q inverse squared. And so this is Q plus Q inverse times 1 minus Q squared minus 1, which is Q squared times Q plus Q inverse. And now you check on the other side, if I apply the Reidemeister 1, then I get a trivial circle as we saw before. And the trivial circle is Q plus Q inverse. And you see, somehow Kauffman was not completely right. So this is not, unfortunately, not the same thing. Okay, but luckily there's a fix. And the fix is the following. Now, before I want to make the fix, I want to do a more complicated example to just show you how to calculate with this Kauffman bracket. So I wanted to do this knot, which we had before, namely this trefoil knot, like this. So when you want to compute the Kauffman bracket of that, you have 3 different crossings. And each of these crossings has these 2 resolutions. So and I just draw them. So for instance, the first picture takes for every crossing the first type of resolution, this cup and this cap. So here down there in the little corner, you see always whether I do the first crossing, the first resolution, which is denoted by 0, or whether I do the second one, which I will denote by 1. So for instance, in the second column, there's always one of the 2 crossings changed with the other smoothing. So I have 1, 1 always. And so in the first case, I changed this crossing in the opposite way as here. So it's exactly different here and everything else is the same. The second one, I changed this one. So they differ here. And the third one, they differ at the bottom. And so the next column would be that I take twice the second smoothing and once the first smoothing. And the last column is I take 3 times the second smoothing. And then you just get, at the end, in each step, you get a number of circles. And for each circle, you get some Q plus Q inverse. So in this case, 2 circles, so you get Q plus Q inverse squared. Here you get 1 circle, Q plus Q inverse, 1 circle, Q plus Q inverse, etc. And here at the end, for instance, you get 3 circles, Q plus Q inverse to the power 3. And this green thing, because I took this smoothing, so this green Q comes always in when I take the second type of smoothing. So here I had once the second times of smoothing, so I get a Q in this column. Then in this column, I get a Q squared because I took twice the second type of smoothing. And in the third column, I get a Q to the 3 because I took 3 times the second type of smoothing. And then you just sum up the columns, you get this expression, which you can just calculate. But now we had this problem that this was not really the correct thing. And now I want to fix this. And the fix is the following theorem. So when I take, so this is the so-called Jones polynomial. When I start with D, oops, what happened here? Sorry. When I start with D, but now D should be an oriented knot or link diagram. So I include an orientation. Then I do the same procedure as before. I take the corresponding diagram where I forget the orientation, D, but with orientation forgotten. I take the Kauffman bracket, and then I just renormalize it a little bit with -1 to some power and Q to some power. So the power is n plus -2 times n minus. And this power is depending on my orientation. So n plus is the number of positive crossings, whatever this is, I will say in a second. And n minus is the number of negative crossings. Oops, too many positives. Okay. So, and this is the statement is that this defines an invariant of oriented knots or links. So that means if we put in extra orientation, then we can fix this problem from above by some extra scalar which we put in. So what do I mean by positive and negative crossing? So I have 2 types of crossings, this one and this one. Say I orient up. Then positive means, so when I take the upper strand and I move it to the lower strand, so I turn it like this. If I go in the mathematical positive direction, then it's a positive crossing. So this would be a positive crossing. And then for the other one, I take the top strand, I move it to the other over to the other one. So that means I move over there. This would be the negative direction. And of course, you should not move it down there because then the orientation doesn't fit. So you have to move it so that it fits with the orientation. So this is positive and negative, and you can just count for this guy how many you have. So let's look at this example, which we had upstairs. Which one did we have? We had this guy here. And let's do this orientation. So this would be a negative crossing. So this is a negative crossing. And so what I get is an extra factor. What is the extra factor? The extra factor is a q to the -2. And this is a plus here, sorry. Q to the -2. And if I check what happens upstairs, it's exactly the thing which went wrong before. So with this fix, I get an invariant of knots. And this Laurent polynomial, so this is inside ZQQ inverse, this is called the Jones polynomial. So now, what has this to do with what we did before? Oh, yeah, maybe I should say something about the proof. The proof is pretty easy. One has just to check the Reidemeister relations. And because this is just a very nice, simple list, this is pretty easy to do. Okay, so now, what has this to do with the stuff which we did the last 2 lectures? So I want to use this now and move to webs. So I want to move or turn knots and links into webs. Because webs is something which we understand maybe better than just these diagrams. Okay, and what is the rule? So I fix n, a natural number. And then the rule is whenever you see a, so maybe I should put one comment before. So maybe I should put this here. So the fact is, given a knot diagram. So let me write one of them which we had before. Like this one. I hope it fits, yes. So given a knot diagram, then we can always slice it into pieces like this after we moved it maybe a little bit around, like this. Oh, last one is not so good. Like that. Okay. So the fact is, given a knot diagram, we can always cut it into pieces of the form identities, just strands, or crossings, like this, or cups and caps. And when you take it oriented, then of course, such that they are oriented. So after you move it a little bit around, you can always find such slices. So that means I can build up my knot diagram in terms of these diagrams. And this should remind you very much on how we build up monoidal categories. We had generators and relations, and our generators, for instance, for temporal leap, were exactly this cup and cap. And for things like Brauer, it was crossings, maybe without under and over crossings, but just crossings and cups and caps. So they looked very similar. And for braid groups, we had these braids. And so for these diagrams, we have now these type of generators. And now I want to go down again. So I want now to turn every knot into a web. And I do this by cutting into pieces and assigning to each piece a web. And the rule is just very easy. I take my natural number n, which is fixed. And then whenever I see a cup, I assign to it this web, this generating web, which we had yesterday. And so it has at the bottom this number n, and then I split. And if you think back at the definition of a co-evaluation, we said this sort of cup diagram is often representing a co-evaluation going from the identity element to V dual to tensor V. So this pointing down is my V and pointing up is V dual. So and this one was standing yesterday when we went to the representation theory of GLN, was corresponding to the natural representation. So you should think of this V corresponding to 1, and then the up is the dual, which can be identified with the n minus first exterior power of V. So this is somehow why maybe this diagram makes sense. And then of course, if I orient in the opposite way, I swap 1 and n minus 1. And if I turn it around, I turn the diagram around. And then for the crossing, I just take the relation which we had from before, from the temporally leap. So this is like in the Kauffman bracket, except that I connect them in the middle. And for the opposite or the inverse braid, I just take, so if I think in terms of the Hecke algebra, connecting the Hecke algebra and the temporally leap algebra, then I have an inverse element in the Hecke algebra, and I can again compute it. So I get just a formula which looks like this. So this is where this comes from. And then you can, if you want, you can compute the difference between these two crossings, and you get a relation like this. And this is often what topologists would call a skein relation, or what people would write down when they define the quadratic relation in the Hecke algebra. Okay, so now, how would the Kauffman bracket and the Reidemeister moves translate into these webs? So how do Reidemeister moves translate into webs? Reidemeister and Kauffman bracket. So let's do the first thing. So in the Kauffman bracket, we had this normalization Q plus Q inverse is the value of a unknot or triple knot. And so if I go to the webs, so this is, I put whatever sort of orientation on it, I would get such a diagram where I have at the bottom n, at the top n, and then I have, so let's just choose one of them, n minus 1 here, say, and 1 there. Or I have the other one here and minus 1 there. And we had the bubble removal, and n, I want to put n equals to 2. So when I put n equals to 2, we had the bubble removal relation, which we proved. So this was equal to quantum 2, or quantum n times this guy. And so this is exactly, this quantum 2 is exactly this Q plus Q inverse. So this translates nicely for n equals to 2. So now let's do R2, the Reidemeister move 2. If I want to draw them in terms of knot diagrams, I have this one is equal to that one. And now I translate it into webs. When I translate it into webs, I have one crossing, which is replaced by that. And the other crossing was replaced by this one. So this was our convention. And if I multiply this out, what I get is, I put this on top of itself, minus Q inverse times that guy, minus Q times this, plus Q inverse times Q, which is 1 times the identity. So, and again, I have this bubble. And again, let's take n equals to 2. Then this bubble becomes Q plus Q inverse. And so I get exactly these things canceled out, and I get the identity for n equals to 2. Okay. And then R3, I get the braid relations. So I don't want to draw them anymore. But the braid relations, they translate on the website into something a bit more complicated. They translate into an equation which looks like this. So I have 3 types of this merging and split. And on the other side, I have it in the opposite direction. So this is similar to the braid relation. So I have on the left, on the right, on the left, on the right, on the left, on the right. And so it's always labeled 1 and 2. Like this. But because when I smoothen a crossing, I get 2 terms. So what happens is I have an extra correction term, which looks like this, plus this guy. So that's just a direct calculation. So now, what the hell is this funny relation? So one explanation of this is again in Hecke algebras, which I will say a little bit later. But let's first look at our web category. So in the web category, I had as a defining relation this thin square switch like this. So if I take this thin square switch like this, and I take the special values a equals to 2 and b equals to 1, then it translates into that thing. So I have here a 2 and here a 1. So they merged 2 in the middle. And on the right-hand side, this b minus 1 just completely disappears. So I have nothing here. This trend disappears. And it simplifies to that side. And I have the identity on the right. And this a minus b is 2 minus 1, which is 1. And then I can do the same thing for a equals to 1 and b equals to 2. Then I get a relation like this. And so if you compare the two, what you see, they are the same thing. Oh, no, I should first do something else. What I can do now, I can put some chicken feet here and split this, and split this, and split this, and split this. So they're still, of course, all the same. And then on the other side, I can put some chicken feet here and split this and split this. So what I created is something which starts at 1, 1, 1, 1. So 1, 1, 1. And it ends at 1, 1, 1. So I can now compare them. So and what you see is that here is the same thing as here by this associativity relation which we had. And so what is left over is this diagram on the left, and these two. And so if you just take the difference of the two, you get exactly the relation here. So that means the thin square switch for a special case implies this relation. So, and if you know Hecke algebras, then you can think of this relation as being the relation of the braid group, except that I take slightly different generators. I don't take the normal HIs, but I take the HIs plus Q. And these are very nice generators. These are so-called Castanistic generators. So the generators are nicer. So in particular, you always have some nice positivity formulas, but the braid relation, unfortunately, looks a bit more complex. Okay. So, but what this says is that we can translate all our relations from the Reidemeister moves into web relations. And so whenever, what we do now, given a diagram, I should maybe write this in the conclusion. So the Reidemeister 3 move follows from the web 2 relation. Okay, and what I left out is the Reidemeister 1. So the left out is the Reidemeister 1. And it again would fit. It would fit up to a normalization factor. So it's the same phenomenon as we had in the Kauffman bracket. So and where did I use now anything about n? I only used anything about n when I wanted to remove this bubble, and when I wanted to match it with the value at the unknown. So if I would say the value of the unknown is the quantum number n, then all the relation would still be true. And so what do I get out of this? What I get is, given an oriented, or maybe not oriented, given a knot diagram or link diagram, or even a tangle diagram. So tangle diagram just means I can have open ends at the bottom or top. Diagram D. What I can assign to it is a web diagram via this one. Let me call it W of D. And then what I can do, I can apply phi of W of D, where phi was this functor from webs in Q to this fund of this web stations of GLN. So yesterday we had a functor going from the web category into this category of tensor products of fundamental web stations for GLN or quantum GLN, if you put in the Q. And so I can just start with my node or link or tangle diagram D, translate it into a web diagram, then apply my functor. And what I get is a morphism between certain web stations of GLN, of quantum GLN. And what are these web stations? These are just tensor products of wedge products. And so the theorem is now the following. And this is true to Reshetikhin and Touraev. And this says the assignment sending D. So oriented, again, I have to take it oriented, not or link or tangling diagram. And then I send it to, so let me call this maybe I of D. I send this to I of D. So this is oriented. I start with an oriented diagram. I forget the orientation. Then I assign a web diagram and then I apply my functor phi. This is up to this normalization, which is minus Q to the n times n plus times, no, n times n minus. No, that's not correct. So it's Q to the n times n minus minus 1 to the n and Q to the n plus. So before we had n equals to 2, and then I would have a 2 times n minus. This was what we had before with a minus in front, and then n plus, which we had before, and then a minus 1 to the, I think, so I'm not sure about this one. Maybe I just put the question mark. I forgot about this exponent up to some minus exponent. This gives an invariant of oriented links. Gives an invariant of oriented links or tangles or not, with the normalization such that the unknot oriented in either way is sent to quantum n. So this generalizes the formulas from before, and this is called the GLN quantum invariant of knots or of tangles, if you want. So this is very beautiful because it allows you to distinguish at least some of the knots. You might not be able to distinguish all of them, but distinguish some of the knots just by passing the web stations of GLN or quantum GLN. So what does it mean now in practice? So let's say we have an oriented tangle diagram. So let me just draw one. This, for instance, this, and I orient it up here, down here, up here, up here. So what do I assign to this? So I assign to this, so remember my rule was, I have these strands, I replace them by some webs. Each crossing I smooth, and the cup becomes one of these mergings. What I do is I get a map phi, which starts from this strand here, which is a down going on, which is a V. Then I have another strand, which is another V. Then I have another strand, which is another V. And then I have a strand which goes up, which is a dual of V, or in other words, the n minus first power of V. And if you want, you can quantize. And then you do this map, and you end up at the strand
second
here.
one also goes up, right?
Second?
The second one is also going up?
The second one
Not
is
just the last one?
this one.
Yeah,
Yeah, this goes up here.
but you didn't put a dual on it.
Do you want me to put a dual?
No, I wasn't sure. For the last one, you said it went up, so you made it a dual.
Oh, yes, I did this wrongly. Let's put this down.
Good.
So I have this, then I have in the middle wedge n of v. That's somehow the outgoing guy here, which we don't draw. And then at the end, I have an up guy, and an up guy was for me an n minus 1. I hope it's correct now. Okay? So, of course, this thing can be very complicated, but you just translate every single step, and then you know exactly what this map is from the formulas I gave you yesterday. Okay, so that means what we have for each oriented tangle diagram like this, we assign to the bottom some module for my quantum group. I assign to the top some module for my quantum group, and for the tangle itself, I assign a map going between them. And the statement is that this assignment of this map to this tangle is up to this normalization in the front is an invariant of this tangle. Okay. So now let's go back to the first lecture. So in the first lecture, we categorified somehow N0. Whatever categorification means. So we realized N0 as a set of isomorphism classes of something. So what I want to do now is I like to categorify this wedge A of V or tensor products of such. So what do I mean by this? So when I categorified N0, I said every element in N0 should turn into an isomorphism class. So now when I'm categorifying this vector space, I could think of every element in this vector space should turn into an isomorphism class. But this is a bit too bad. What is a better notion is to do the following, to work with the Grothendieck group. So a good way to somehow count isomorphism classes is the Grothendieck group. And when you look back to the first lecture, we had a little bit problems when sometimes our multiplication or addition went out of the category. If one would do it correctly and use the Grothendieck group, then things would work nicely. So what is the Grothendieck group? So I have K0 of C. C is some category, which should be abelian or triangulated, if you know what that is. So abelian or triangulated just means I have a notion of short exact sequences or triangles. And then the Grothendieck group is nothing else than I take the objects in my category up to isomorphism. And then I take the free abelian group over this. So I just take formal set linear combinations. Modulo the relation of short exact sequences. So C is equal to A plus B. So the isomorphism class of C is equal to the isomorphism class of A plus B if there is a short exact sequence, or in the triangulated case, a triangle of the form A goes to C goes to B. So if your category is semi-simple, then it's the same thing as a split Grothendieck group, which we saw more often. Otherwise, it's you force it somehow to be semi-simple. Like every short exact sequence should like how behave like it would split. Okay. So now, what does categorification then mean? So let's try to do this. So I want to categorify this space here. And categorification means I want to find a category C, let me denote it C upper A, such that when I take this Grothendieck group, so this is a Grothendieck group, and maybe I should have written it here. When I take this Grothendieck group and I tensor with the natural numbers, over the natural numbers with the complex numbers, I get a vector space. So this is a vector space. So I will do this also here. And categorification for me at the moment means that my vector space should be realized as a Grothendieck group of a category, which I just change by the scalar extension to turn it into a vector space. Okay. And then what I want to do on top, I want to somehow categorify all these wedges. And I want to make them compatible or fit them together such that whenever I have a map here, phi, so this is a UQ GLN homomorphism, like coming from, for instance, such a tangle, then I would like to have an induced map here such that the diagram commutes. This should commute. So by this, I mean, when I go via this isomorphism to here, and then I want to find this map there such that when I start from here going down and over there, it's the same thing. And this map should be not just a map between vector spaces, it should come as somehow the induced map from a functor. So this phi is supposed to be a functor phi from this one category CA to the category CA prime, which is exact. And then whenever this is exact, it induces naturally a morphism between the corresponding vector spaces. And so I would like to find such a category. I would like to find such functors such that all this stuff commutes. And this is what I mean by categorifying this vector space and categorifying the morphisms. Okay. And so in particular, we would like to do this for the maps coming from this invariance of tangles. So, but before I do, I explain a little bit about how one can do such a thing. I want to make an example as a warm-up. So what is the Grothendieck group of k vector spaces? So finite dimensional k vector spaces. So I claim the Grothendieck group of finite dimensional k vector spaces is just the integers. So I think we computed this also in an exercise. So how does this isomorphism work? Whenever I have an integer m, so let's say m is a natural number, not 0, and I take either this number or the inverse, then I can take the corresponding k vector space of dimension m, take its isomorphism class in this group, and either take it positive or negative. So because formally I have a negative in this group, and so this negative makes sense. And of course the 0 goes just to the class of the 0 vector space. So now I could of course use this and take many copies of this category to find something here. This would be one possibility, but I would like to do something else. But before I do this, I would like to sneak in the little q. So we sneak in a little q on the left-hand side. So, and we want to have that this thing is an isomorphism of CQ vector spaces. So, but how do we get CQ vector spaces out of it? So let's first do an example for that. So let's take now finite dimensional graded K vector spaces. So each finite dimensional vector space is an additional Z grading. So then I claim the Grothendieck group of that is not Z anymore, it's Z adjoint Q inverse. It's exactly this ring which we had before from this Jones polynomial. And how does this work? So when I take plus minus m, so m is a natural number, then for this I would assign the isomorphism class of the vector space of dimension m. Now if I multiply this with q to the r, then I just sneak in this r here, and this means I put c to the m in degree r. Or if you want more precisely, multiplication with q to the r on the other side corresponds to a shift of the grading in this category of finite dimensional graded vector space. So I shift up the grading by r. And I claim this gives an isomorphism of Z modules. I should write this like this. Okay, now I can define K0 of these finite dimensional graded vector spaces. I can tensor over ZQQ inverse with CQ, and what I get out is this thing is a CQ vector space. Yeah. So and if you believe this, then what I would like to do upstairs, I would like to sneak in here. This should be a graded abelian category. So it should be some sort of, for instance, modules over a graded algebra. And so this should be a graded abelian category, something like modules over graded modules over graded algebra. So I have some grading shifts. And then I put here QQ inverse, and I put the CQ. I put here QQ inverse, and I put the CQ. And then it makes sense to say this should become a CQ vector space isomorphism. So this is the whole thing which I want to do. Okay. Right. So now, as a remark from last lecture, to fit all this together, it's enough. It's actually enough to categorify this skew-Howe duality. So it's enough to categorize skew-Howe duality. Or it's even more to categorize skew-Howe duality. Skew-Howe. So what was this skew-Howe duality? This skew-Howe duality, remember, was I had this n-fold wedge product of the natural representation for GLN, or the quantum group if you prefer, outer tensor product with the natural representation for GLD, and maybe quantized. We had this. And we had that this decomposes as a module from the left into a direct sum of these wedges. So this is as UQ GLN module. And for the right thing, so as UQ GLD module, it decomposes into another wedge. Not B, sum over B, where this A was a tuple of length D, and the sum of the entries is N. And here this was a tuple of length N, and the sum of the entries was N. Okay. So and in particular, in this sum, we have all possible wedges. So if you just can categorify this thing or these guys and the morphisms between them, of course, we solve our problem from above. Okay. So now I want to sketch how one might do this. So behind this is it's a pretty complicated construction, but I want to give at least an idea how one does it. So and often you have to understand the combinatorics well enough. And if you understand the combinatorics well enough, then you can cook up an interesting category. If you also understand enough representation theory coming from some other side. Okay, so what do I want to do? So I want to take a standard basis vector. A standard basis vector in wedge AV. So this is inside here. So and I want to realize this stuff as a Grothendieck group of something. So the standard basis vector is supposed to get mapped to something in the Grothendieck group. And so something in the Grothendieck group, ideally, it's mapped to an isomorphism class of an object. So what I would like to do, I like to assign to this an object in some category. in CA, whatever CA is. Okay, let's try to do an example. So I want to take V and I call it V lambda. This is V4, wedge V2, tensor V2, wedge V1, tensor V1, wedge V2. So my N in this case is 6, I guess. And I want to put the tensor at the end. Okay, so my little n, it doesn't matter. You just have to make it big enough so that you have at least n equals to 4. So what do I want to do? So if you look at such a sequence, what I can say, each of these pieces between the tensors turn into some tuples of numbers. And so these numbers are tuples of numbers which are always decreasing, because I picked the basis of my wedge and I always wrote it so that they are decreasing. So if you want, these guys are dominant integral weights for the Lie algebra GL, whatever you are. Dominant integral weights for, in this case, GL2, GL2, GL1, GL1. And I should maybe make them orange because they have nothing to do with the red GLN yesterday or the green GLD yesterday. So it's yet another GL. So yeah, it's just if you write a weight in the epsilon basis, it's decreasing integral numbers. So now for each such dominant integral weight, I have a unique irreducible finite dimensional representation. So what I can assign to this is an irreducible finite dimensional representation, L lambda of GL2 times GL2 times GL1 times GL1. Okay. So now let's draw my GL2. So this is A1 is equal to 2, A2 is equal to 2. I draw this now as a so-called levy in a bigger guy. So these are block matrices. 3, 4. So these are block matrices in an n times n matrix, because the sum of the AI's is n. Okay. So let me call this black thing L of A for levy depending on A. And so this sits inside GL capital N. Okay, now I can take this representation and I can induce it up to the whole GLN. So I induce it up to the whole GLN. So I do exactly induction like Monica did for the symmetric group. But I have to take it for this LA, for these block matrices, and first extend it by 0 to this part. So and the black and the blue one I call P of A for parabolic. So this is black plus blue together. So I extend by 0, and then I have a representation for PA, and then I induce up. So if you want to write it out explicitly in terms of universal enveloping algebras, it looks like this. And so there's nothing quantized. So this has nothing to do with the quantization and the GLN before. So this module, it depends on lambda, and of course it depends on A. And this thing is called a parabolic Fermat module. One can define somehow a category around it, OA, around these modules. So ideally, you would take just a semi-simple category, which has these guys as simple objects, but this doesn't exist. But what you do, you take a category where these guys, when you pass to the isomorphism classes, form a basis of the Grothendieck group. So this is a so-called category O. It's a highest weight category with these things as standard objects. I don't want to define this category, but such a category exists, where these isomorphism classes of these guys form a basis of the Grothendieck. And the lambda is, of course, running through all possible indices coming from my basis vectors. Okay, and then the statement is, when I want to categorify the sum of wedge A of V, like this, isomorphic to wedge B of W. So then I first refine this by passing to the weight spaces. I pass to the weight spaces, and here I also pass to the weight spaces. So the weight spaces for one side of the skew-how duality are the modules for the other side. So, and then categorification means I get something where when I take K0, I go there. And so this is just a direct sum of these category O's, where I want to fix the B's, respectively the A's, and the sum over all A and B. And from the construction, what is this B? This B is telling the weight space in here. So the B is just giving you all the sequences where I fix how often the ones and the twos and the threes, etc. occur. And so I just have the corresponding parabolic Wörmer modules where I just fix how often the ones, two, etc. in the corresponding weight occur. And so I get such a category. And this is an abelian category. And the Grothendieck group is exactly then this guy. And the claim is, so there's a theorem that there is an equivalence of categories after you pass to the, at least to the bounded derived category. So it's not an abelian category, but it's after you pass to the bounded derived category, and there's a graded version on it, which somehow gives you this skew. So the graded version is something complicated. One needs some kind of perverse sheaves categories. So this is related to Laura's talks on Hecke algebras. And then when I have this graded version, I can sneak in the Q. And then this isomorphism becomes some sort of Cauchy duality. So this is what the result says at the end. So all this is very abstract, but what does it give you? It gives you for each vector space a category, for each morphism, and I should write this, and the functors and the morphisms between GL n modules, or QGL n modules, lift to functors. So what we have at the end we have the following. What we get is, given a tangle, an oriented tangle, what we assign to it is a web, and what we assign to this is a morphism of UQ GLN modules, and then we assign a functor. And so why is this better than having webs? So let me show you a picture. Assume I have assigned something to a knot, for instance, to this one here, or to this one, or to these ones, which is a functor. Then you might ask the question, can we assign something which corresponds to this cobordism? So cobordism is something which goes between these trivial knots. And when you do this categorification, this is possible because categorification turns a knot into a functor, and you can go via natural transformations between functors. So one might ask the question, can I assign to such cobordisms a natural transformation? And when you think of what are cobordisms between tangles, there are a list of moves like this, where you draw on the left-hand side a surface, which which you can only see in these pictures by taking this. So when you would take this surface here and you would cut horizontally all the time, it starts looking like this at the beginning. Then it stays like this for a while, and suddenly it becomes one circle, and then it stays one circle. So it's like a movie move when you walk through. And these pictures here, they give you movie moves of surfaces going between these complicated tangles. And there's a list of movie moves which you have to check to get all the Reidemeister moves realized in terms of surfaces. And so this is a long list. But the claim is that indeed one can assign to each such cobordism going between tangles some natural transformation between the functors. And so the outcome at the end is you can have, on the one hand side, tangles, and you might even color them by colors, each strand, corresponding to sequences of colors at the top and at the bottom. You assign to the sequences, corresponding sequence, move the colored tangle into webs in the way how we did it. And then you can ask the question, can I pass to two-dimensional things going between these tangles? And on the website is also possible. These are then surfaces between webs, which look like this, pretty complicated guys. And then the categorification allows you to send these sequences to categories, the webs or tangles to functors, and the cobordisms to natural transformations. And so what you get at the end is some sort of two functors. So functors between two categories in this way. And so let me just finish by saying categorification in this example allows you to climb up by one dimension. So we don't even only get invariance of knots, but we get even invariance of two-dimensional things, of surfaces being either between webs here or these complicated pictures here. These are the cobordisms, so surfaces going between tangles. And this is where I want to stop. Thanks very much for listening.
Let's thank Katharina for this talk and for her wonderful lecture series. I think that provided some really great insight and perspective on categorification. So thank you. And any questions for her?
But was there anything in the chat I should answer?
There was a small typo where an A should have been an A prime, but I think
I had a small question too. Well, you can go find the typo is higher up above.
it's a little bit higher.
No.
Oh, here, yeah, it's on the bottom right.
I see it. Thanks. Sorry.
When you define the parabolic category O that you got out of there,
yes.
So in the vector space that we started with, this wedge A,
yes,
because we were starting from GLN, the subscripts like the V4, 2, etc. Like 4 had to be bounded by n. It's 4,
yes.
2. You're saying it's like the highest weight. But when we're doing these L lambdas, is there also, do you have to cap off the lambdas there in this way, or you can just do it and then somehow the statement still makes sense because you put this weight space B on things?
Yeah, you just somehow, you start from the vector. So you already say what you allow, and then you construct the lambda. But you could, so if you increase the n here, the little n, then you could take a different category O, and the first category embeds into the other one. And the combinatorics is exactly the same thing. So if you would pass to the Grothendieck group, it would be just the same thing.
Mm-hmm.
Yeah. And so the point of these categories, which I somehow put under the rock, is that they are not semi-simple. They have lots of interesting structure. And so this Grothendieck group here, passing to the Grothendieck group, really forgets a lot of stuff. So that means the combinatorics is much less rigid or has much less information than the category itself. And so what turns out on the categorical level, you can distinguish, for instance, the unknot from every other knot. And you for the Jones polynomial, this is not known, or for this GL n invariance, it's not known whether this is possible. But on the categorical level, one can prove, one can distinguish the unknot from all the other knots. So it is a much better invariant. Yeah.
I've heard of these things called foams, which are somehow cobordisms between webs.
Can you say again? I only understood half of it.
So I've heard about foams, which are cobordisms between webs. Does that fit in this picture?
Yes. So these foams, wait, where's my picture? So these foams are these guys. Yep. So and what is a foam? A foam is a morphism between two webs. And again, when you define you can define the category of forms in terms of generators and relations. And each generator gives you then a morphism, a natural transformation between two functors. And you can just define these natural transformations. And then what you have to check is that the natural transformations satisfy the relations of the forms. And this is what one does. And the hardest thing is to draw these forms. Yeah.
Can you explain one more time just scroll up just a little bit?
Mm-hmm.
How you got from, so the first line, I'm sorry, down. Yeah, right here, where you have sequences, sequences, and then derived categories.
Mm-hmm.
How you get from the derived category part, so are you starting there with the complexes and then going, and then how you get to the next line again?
So this one?
Yeah.
Okay. So here I have a derived category, whereas here I have sequences of numbers, which I call colors. And then having two sequences of colors. So for instance, in this example down here, it would be green, red, blue, blue, blue. And on the bottom in the similar way. I have two derived categories here. So one corresponding, so let's say on the top I have the colors A, on the bottom I have the color A bright. Then I would have a second category, which looks like this. And then the tangle is supposed to be a functor going between them. And you do it exactly as we did it before. You first write the tangles in terms of elementary pieces, and then you assign to each elementary piece a pretty easy functor. And then you check that these pretty easy functors satisfy the relations you want to have. And so this gives you then a probably complicated functor associated to each tangle with these colors. And so the functors are things like this A up there, for instance, I can change. So if you think back, how did this A come in? This A came in by choosing this sort of levy or this parabolic. And of course, there is some correspondences going between different parabolics. So if you refine a parabolic, it will be a subalgebra of a bigger one. And you use them to do some induction and restriction to go from one of these categories to the other. And because induction and restriction is in contrast to the symmetric group, you're not exact, you have to derive, and therefore you have to go to derived categories. And therefore you need to use complexes.
Mm-hmm. Wow, thank you so much.
And then for the skew-how duality, you might want, this is maybe something I should mention. For the skew-how duality, you would like to have another commuting action. And this also exists on this category. And I think this is the only categorification I know of skew-how duality where you can really see on the same category both actions. And this other action is actually much easier. It's just tensoring with finite dimensional representation. Certain finite dimensional representation, maybe take a direct summand. And then you can see both actions on the same space and they commute with each other. Yeah, and yep.
Any other questions for Catharina?
I had a small question. So does this only work for the two-dimensional setting, or can you keep going?
You mean in terms of cobordisms?
Yeah. And the webs, yeah.
So at the moment, yes. it only works for the two-dimensional setting. So a big question is, how can we go further? And so it's believed if one puts all these things together. So what we categorified at the moment are modules over some Hopf-algebra or some quantum group or something. But we didn't categorify the monoidal structure. So the hope is when one categorifies the monoidal structure properly, that one can go one dimension higher. And then one is in dimension 3. And dimension 4, so far nobody knows what a TQFT in dimension 4 is. And nobody knows an example of a TQFT in dimension 4. And TQFT means exactly going up to dimension 4. So physicists look for this since years. And so there's no answer at the moment. And of course, the hope is that one might be able to continue, but at the moment it's not clear. And also the another problem is on the level where I am now, I use 2 categories and 2 functors. And this can be written down still pretty elementary. But going to 3 functors and 3 categories, there's already not a unique definition for what a 3 category is. And if you go higher, you have to work immediately with much more complicated structure. So there is a big step between 2 and the rest.
Okay, thank you.
I have another like very random, very nonsensical, I don't know if that's a word, question. And that is, does it make sense to try to work with enriched categories, like enriching in some structure that makes sense? I don't know.
Okay, so I'm laughing because I'm actually at the moment working on a project where I think we can get out dimension 3 properly by enriching categories. So we work with DG categories, enriched categories. So that means we have objects, something easy, like here, these sequences, and then the morphisms are
natural transformation.
The morphism objects are categories. So a morphism, so for instance, a morphism from M to N is a category of, say, AM, AN bimodules for some algebra or ring AM and AN. So the morphism spaces are difficult. So we enrich, if you want, we enrich in categories.
Mm-hmm.
Except that we do a little bit more complicated than categories. But I totally agree, this is what one has to do.
Yes. Sounds a lot of fun.
Yes. But the problem is, so one has to be careful what it means to enrich in something.
Mm-hmm. And do you also get like, are you able, when you are moving into like enriching, like how able are you to work with diagrammatics when you're in that stuff?
Actually a lot. So I would say at the moment, everything we can do really from the representation theory side can only work because we have diagrammatics. So the point is these categories which I wrote down here in an abstract way, they can be described more concretely or more explicitly in terms of circle bimodules, which are certain bimodules over commutative rings. But this circle bimodule category has a diagrammatical description again. It's a 2 category and it has a diagrammatical description. It's a strict 2 category. And the fact that you have a strict 2 category makes life much, much easier. And then you work with the diagrammatics.
That's the question. If you have, are you able, you're only working with the strict, right? Because is it possible to be working with the same kind of diagrammatic in terms of the enriched world if you have non-strict stuff? Like
no, if you have non-strict, then, so for me, diagrammatics is somehow equivalent to being, not equivalent, but diagrammatics means strict.
Okay, yeah. I have the same idea. That's why I was asking. Thank you.
And strict is much, much easier.
Hi, this is Dula. I hate to break up this wonderful discussion. It's so interesting, but I'm slightly worried that it's time to wrap up and thank Catharina for this fabulous series of lectures. And perhaps you can continue some of these discussions. We're going to have a meeting in Gather Town, but after that, if people can hang around, it's possible to discuss a little bit.